Professor, can I ask you a question?
Oh, Travis, are you saying something?
Yeah. I have a quick question.
Hang on. We have the opposite problem today. The volume is really low.
Okay.
right.
Here's I'll get closer to my laptop. So
Okay.
I was looking over the solution that you posted,
Yep.
and for the challenge problem, it seems like some of the vectors that like you solved for didn't go into like the final matrix.
Mhm.
I was just kind of curious about that because for like the last one, it was like 0.395.124 and then 0.911, but
Yeah.
put like 0.356, negative 0.212, and 0.911.
I would have to check it again. It's honestly it's been a while since I've looked at that one.
Okay.
Yeah. Let me I'll look back at it in my office hours, and then I'll get back to you on that one.
Okay, yeah, I'll probably stop by online.
Okay, sounds good.
All right, thank you.
Yep. All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Hang in there. Busy week. I'm sure we have a midterm this week. I'm sure you guys have a lot of other deadlines. So it's the last sprint for Thanksgiving. Okay, hopefully everyone got my email today. I did post the solutions for homework 5. I know it's a little bit early, but I did want to make sure I get it to you guys before well before the midterm, so you can use it to help you study. Especially because inverse dynamics and transformation matrices are going to be a big part of the midterm. So I want to make sure that I get that to you guys. Our midterm exam is this Wednesday, so make sure you guys are here for that. And we have something unique this year. We actually do have class on Monday, the Monday of Thanksgiving week. So I will be here next week. But as always, the lectures will be streamed and recorded, and so I know it's kind of a bummer to have to work that day, but there are options for you guys to catch up on the lecture if you have other plans during the week, like I did before I had to cancel them. So because I had to come to work on Monday. So okay, all right. So today we're starting something new. So if you count today's lecture, next Monday's lecture, we only have 4 more lectures to go before our final week and our final presentations. So I'm hoping that I can finish up this topic by next Monday, and then after Thanksgiving we'll go over something new that I haven't gone over in this class before, which is biomechanical simulation. So there is an open source software called OpenSim. I've been wanting to use it in this class for a couple of years now, but I just kind of ran out of time. But this semester, I was able to hopefully carve out 2 lectures where, Monday after Thanksgiving, we'll go over some of the theory, and then Wednesday we'll actually do a software demo, where, hopefully you guys can use that for your final projects. That's what I'm hoping for. Okay. Regarding the final project group, so I think most of the groups are mostly set. There's just a few more people that don't have groups. I think what I'm going to do, so if you don't have a group yet, you'll probably be getting an email from me this evening, and I will, I'll just kind of be putting you guys all together in one group. So I think it's just a few more people in the class. So I think everyone else's groups is pretty much set at this point. Okay. So if you're not in a group yet, just keep an eye out for an email from me, and and then just look forward to working with your new group. All right. Any questions I can answer before we get started for today? Okay. All right. So let's go ahead and get started. So the topic for today is muscle force optimization. All right, and so this unit here is kind of the end of our dynamics unit. And so it very much kind of goes together with our human motion capture analysis as well as our inverse dynamics, okay? So the idea with muscle force optimization is that we are at a point right now in our dynamics analysis where we want to be computing muscle forces, right? So after an inverse dynamics analysis, right? What do we obtain after inverse dynamics analysis? After inverse dynamics, we're able to compute the net forces and net moments that are occurring at each joint, that are needed to cause a motion. Okay. Okay. And so, I think when we first introduced inverse dynamics, that we talked briefly about what it means to be a net force or a net moment, but let's just kind of review that again. Okay. That means that, during a motion, so let's say that, we have an arm joint here, or not an arm joint, an arm. Okay. So an arm consists of the shoulder joint, right? We have an elbow joint, and we have a wrist, right? So those are the three main joints of the arm, right? And then we have the hand after this, I guess, as well, right? So after inverse dynamics, as this arm kind of goes through a motion, so let's say it's going through a jumping jack or something like that, right? We're able to compute, the net forces. So we have forces at the wrist, a moment at the wrist, right? Forces at the elbow, okay? And then for the shoulder as well, right? Okay. So what do these forces represent? So, these forces are not coming out of nowhere, right? So they're not phantom forces. There have to be things that actually exert these forces, right? So what creates these forces in the body are the muscles, right? So we have muscles that are attached over your joints, over your limbs, right? So they're the ones that cause these forces to occur. Right? We just haven't made that leap yet. We haven't made the leap in terms of, we have these forces, what are the muscle forces that actually cause these things, right? Because what's the issue? So, at any given joint or any given limb in the body, we have a lot of muscle redundancy, right? We have a lot of muscles that contribute to a certain motion, that contribute to a joint. And so these forces that we computed can be created through any combinations of all of these redundant muscle forces. Right? Okay. And so we've actually already done an example on this. And so if you think back to our static analysis of the upper extremity way back, so I think this was about a month and a half ago, we saw that in the upper arm, we have three muscles that are attached there. So we have the biceps brachii, we have the brachialis muscle, and the brachioradialis, okay? And so a situation like this, all three of those muscles can contribute to things like the force at the elbow or the moment at the elbow, okay? So technically, you can take the techniques that we're going to learn now and actually apply them back to our static analysis too, right? Because this was an issue back in static analysis as well, right? And so back in static analysis, if you kind of remember that far back, we kind of made the assumption where, the amount of force that a muscle exerts is directly proportional to its cross-sectional area, right? And, and at the time, that was fine. And at the time, that was what we needed in order to solve our equations, right? Turns out, the reality is a bit more complicated than that, right? And so there are different factors that the body may use in order to choose how the muscles split up the load. And believe it or not, your body does have the ability to do that. So most muscles, what we kind of characterize as different muscles in the body kind of mostly depends on how your body can kind of connect to it via the nervous system. Okay. And so if we kind of distinguish different muscles, usually your body has the ability to kind of innervate or act on them, independently. Okay. So there's some different factors that can that your body can use. So some of these factors include things like energy consumption. Okay, that's usually a big one. So energy is a resource that your body usually pretty careful about. Generally speaking, when your body goes about its business, it usually tries to do so in a way that conserves as much energy as possible. Okay. And so if there's a way that they can kind of divide the load between the different muscles that conserves energy, that's always going to be, something good for the body in the long run. Okay. Another thing that your body accounts for is the fact that, the different muscles in your body have different geometries. And so they have different moment arms, they have different attachment angles. And so each one of those is going to affect a motion in a different way, right? And so, your body's going to account for that. And maybe they give more of the load to certain muscles that can produce the motion or produce the force more effectively. And so that's another thing that's accounted for. Okay. Right. Another metric or another kind of consideration that your body may use is performance. Okay. Sometimes you're in situations where energy consumption is not that important. Maybe you're being chased by a bear and you're just trying to get away from the bear as quickly as possible using every single resource that you have imaginable, right? So sometimes performance is most important, and that's gonna change how your body kind of splits the work between your different muscles. Okay, you're probably going to use most of your fast twitch muscles in that situation. Okay. All right. So these are just a few different considerations that your body may use, right? I bring this up just to illustrate the fact that this is not an easy problem, right? It's not a straightforward way to go from an inverse dynamics analysis to computing, which individual muscle forces are responsible for causing a motion. And honestly, for the vast majority of this class, we've kind of been skirting around this question. And so we've been either making assumptions or just kind of, computing other things. But, the actual task of determining, or I would say predicting, which muscles are acting in a certain situation is not easy. And so to deal with this, we have to use actually a new set of tools that you likely have never used before, unless you're in my 454 class. Right? And so to tackle these kinds of problems, we have to use a mathematical technique known as optimization. I'll shut the door. Give a second. I'm going to give a witty quip right there, but then, the nice lady from the building helped us out earlier, so I shouldn't say anything bad about people in this building right now. Okay, so this is actually a very interesting topic to include in this class because for those of you who are in my optimization class will know that it's going to be impossible to cover all of optimization over the course of 2 lectures, and that's not what I'm going to attempt to do. But there is enough to learn about optimization in terms of how to use it as a tool, where you can use some built-in algorithms or some built-in techniques within MATLAB, within Python, um, to solve these kind of biomechanical problems. And so that's mostly my goal, is to kind of introduce enough of the terminology, enough of the concepts of optimization so you can use it as a tool, rather than 454. 454, we're more about, how these algorithms actually work. So we're not going to get into that stuff. We're just going to be able to learn enough to actually use it. Okay. And even for those of you who are in my 454 class, I think you'll find these next few lectures pretty interesting as well. It's not just going to be a review of everything that we've done. And so you're going to get kind of as much of a practical kind of perspective on optimization as this is as practical as it gets. So, how we think of problems, how we frame them, and most importantly, how do we actually use the built-in MATLAB codes, which I haven't told you about in 454. So you may be upset with me after these next couple lectures, but I think it'll be interesting for everyone in this class. Okay. All right. Any questions on this so far? Okay. All right. So what is optimization? So let's give a brief introduction to that. Okay. So optimization can almost be seen as kind of a kind of like an opposite of algebraic systems. Right? And so if I were to sum up optimization in a nutshell, it's a way for us to solve mathematical systems where we don't have enough equations for all of the unknowns. It would be really nice for people in this building. All right, because usually, what you've usually been taught, from your math courses and your engineering courses, probably from your first steps here in college, is that, in order to solve a mathematical system, you have to have the same number of equations as unknowns, right? They don't necessarily have to be algebraic equations, but algebraic equations are kind of the simplest to do, okay? And that's great when that happens. But in a lot of practical situations, are going to run into, situations where, there are more variables or more unknowns than you can come up with equations for that system, okay? Okay. And so our muscle problem falls into this category really, really well, right? Because typically, when we solve, think back to our static situation, right? When we did biostatics, we mostly had three equations for every problem that we had. We had some of the forces in the x direction, some of the forces in the y direction, and the sum of the moments around a certain pivot, right? If we only had one muscle force to solve for, then we were good because we could use two of the equations to solve for the joint reaction forces, and then our last equation could be used to solve for the muscle force. Okay. But if you had more than one muscle force that's acting on a situation, we just didn't have enough equations to solve for it. Okay. Optimization gives us a way to do this, right? Okay. But it's not magic, right? And so it's not kind of a catch-all. So there are rules to using optimization, and there's kind of best practices. Okay. Okay. So what I want to do is, I wanted to kind of introduce some of the concepts and some of the terminology that we use. Okay. Okay. So first, let's recast our unknowns here. Okay. And so in optimization, generally speaking, the unknowns, we call those the design variables of the system. Okay. And so the objective of any optimization problem is to compute the optimal values of these design variables to satisfy the system as well as we can. Okay. And so it's important to remember that in optimization, we still have equations. And so it's not going to be just chaos. So there are equations that we do have to satisfy. It's just that, we're not going to be able to satisfy all of them at the same time as best as possible. But, usually there is a solution that exists that does its best to satisfy the solutions as much as possible. Okay. All right, speaking of equations, there are actually a couple of different types of equations that we can satisfy in an optimization problem, right? So not all equations are treated the same in optimization. Okay, so let's talk about the types of equations that go into an optimization problem. And by the way, we're gonna do a lot of examples today just so that you can illustrate this, okay? Because for those of you that are seeing this for the first time, it's a lot of terminology, a lot of kind of jargon, and so it's kind of hard to visualize it. So I want to make sure that we do enough to kind of visualize everything. Okay. Okay. So the first type of equation that I want to go over are what's called constraints. Okay. And so in any optimization problem, you're usually going to have more than one equation that you want to satisfy. But it's important to kind of pick and choose between those equations. And so there are some equations which we can consider are nice to satisfy. So they're kind of nice to have. So you can almost think of them as like luxuries. But there are other equations where, there's no negotiation. No matter what, our variables have to satisfy these equations no matter what. Okay. So those are what we call constraints. So constraints are equations that must be satisfied by our optimal solution. Usually if you're given a mathematical system, technically all of your equations are constraints. Think back to when we did statics, right? So we did our sum of forces, our sum of moments. Technically all of those are constraints because we said all of these equations must be satisfied, right? But in optimization, we make the distinction between, constraints versus our other equation here, which is often called the objective function. Okay. So the objective function, this is an equation that, usually in optimization, we don't seek to satisfy, but instead we either seek to minimize or maximize the value of this objective function. Right? And the objective function actually serves a pretty important role in an optimization, right? And so in optimization, since we don't have enough equations to specify all the unknowns, technically there are an infinite number of solutions to an optimization problem, right? And that's, you could state that even without learning anything in optimization, right? If you have three unknowns and only two equations, right? Technically, there are an infinite possible combinations of those three variables that will satisfy those two equations, okay? But that said, there's even though there may be an infinite possible amount of solutions, there are some solutions that are better than others. Okay. And so the objective function kind of serves a very important role in that it gives us a way to compare, different values of our design variables to see which combinations are better than the others. Okay. So these are the basic building blocks of an optimization problem. You have your design variables. Those are the variables that you want to optimize or find their values on. You have your constraints. And so these are equations that must be satisfied no matter what. And then you have your objective function, which is what you either want to minimize or maximize. And this gives you a way to compare different solutions with each other. Okay. All right. So I have a kind of a fairly contrived example next. But before I to kind of illustrate kind of all these concepts, but are there any questions on this so far? Okay, all right, so let's do an example here. Okay. This one's going to be no math at all. This is mostly just to kind of illustrate these different concepts here. Okay. So one interesting optimization problem that you can think of that you can probably test without any paper at all is to, let's say that we want to find the optimal combination of pizza ingredients that go onto a pizza that satisfy not just yourself, but also, your best friend. I actually have a very relevant story for this. And so, I wrote these notes, over 2 years ago. But just last week I went to Blaze Pizza with my wife, and we had to get two separate pizzas because we had different ideas of, what an optimal pizza is. But she's never tried hot honey before. So she wanted me to get hot honey on my pizza so that she could try it without fully committing it to her pizza. And so, I go to pick up the pizzas, and then, our pizzas kind of look similar. So I said, "Oh, can I get hot honey on that one?" But then it was actually her pizza, and so she was mad at me for the rest of the night because I put hot honey on her pizza. So very difficult problem. And so, maybe I should run an optimization study on that to see. Okay, so let's take this problem here and let's relate it to all of the terminology that we just talked about here, right? So the main terminology that we talked about are the design variables, the constraints, and the objective function. Okay, so let's see if we can label all three of those things in this kind of made up scenario that we have here. All right, so let's talk about design variables first. So design variables, those are the things that you want to optimize or what you want to determine from your situation. Okay, and so in this case, the design variables are going to be the pizza ingredients or the pizza toppings, I should say. Okay. All right, so next let's go over the well, we'll go in order. So let's go over the constraints. Okay. So remember, constraints are equations, or in this case, conditions that must be satisfied no matter what. Okay. So no matter what, you can kind of set a baseline with your friend. A pizza has to contain at least these elements, right? Right. And so we can say a pizza must have, it must be, made of a gluten crust, right? Thankfully, I don't have a gluten allergy, so I can eat all that delicious gluten. Right? We can say that our pizza wants to have red sauce. If I can spell sauce. And the pizza has to have mozzarella cheese. Okay. So no matter what, no matter what pizza we come up with, these are conditions that must be satisfied. And so these are some of the constraints that we have on our problem. Okay. You can also set constraints on the other toppings that cannot be there. Okay. Right. So either something that you may be allergic to, or maybe something that you both don't like, or maybe something that one person strongly dislikes so much that that they cannot have. So like let's consider probably the most unreasonable pizza ingredient out there, pineapple. Right. So you can set constraints on those in terms of your pizza cannot have this ingredient. Okay. All right, so now that we have a baseline of what the pizza has to have and what the pizza cannot have, let's talk about how we're going to rate the pizzas. And so that's going to be our objective function. Okay. So remember, the objective function is not something that it's not an equation per se that you can satisfy usually. but it's a way for you to compare, which combinations of design variables are better than the others. Okay. And so in this case, the objective function is going to be taste. Okay. And for the sake of being able to run an optimization, we have to quantify the taste. And so, maybe you taste the pizza and you give it a score 1 out of 10. Okay. So that's the setup of our optimization problem, right? So we've defined the design variables, we've defined the constraints, the equations or conditions that must be satisfied, and we have a way to basically, rank or compare, different combinations of the design variables. Okay. So we're going to take this framework and we're going to apply it to our muscle optimization problem and see kind of, how this will apply. Okay. All right. Any questions on this? Usually when I bring up the pineapple thing, I get a lot of disagreement from, but I guess you guys are all like me, so you guys all hate pineapple pizza. Okay. Oh, actually, before we get back into biomechanics, let's talk a bit about how we actually solve these optimization problems. Okay. All right. So solving an optimization problem is quite different than your typical, algebra or mathematics type problem. Okay. And so usually for most practical problems, we use what's basically can be described as kind of like an educated guess and check approach. Okay? I'll call it strategic guess and check. Okay? And so usually what happens is that, it's impossible to look at an optimization problem and determine the optimal solution, straight away, without trying it. And so usually the way it works is that, um, you're going to propose um, a combination of values for the design variables. Okay? So that's essentially the guess checks. And so you're basically just going to guess, the which design variables are going to satisfy your equations the most. Okay. The next thing you're usually going to do is you're going to check to make sure that your guess or your proposition here satisfies all the constraints. Okay. Usually, if you're kind of smart about how you suggest your design variables, usually that's going to be the case. But it's good to check regardless. Okay. All right, and so if your guess here satisfies all the constraints, next thing you're going to do is you're going to compute your objective function using the values of the design variables that you guessed. Okay. So this part right here is the check. Okay. So actually, let me go back up here. So this up here is the guess. Okay. Then after you guess, you check. Right. Then based on your objective function value, you're going to see, right? So this is an iterative process. So that means we're going to be repeating this flow chart over and over again. And so the next thing you have to check is to see, if this guess is better than your previous best guess. If it is, that's great. Then we save it. If not, no worries. We just throw it out. Okay. All right. And let me zoom out here just so you can kind of see everything. Okay. And so what you do from here is that you just come right back up to the top, right? And so you just kind of repeat this. Okay. So for those of you in my 454 class, we would consider this to be kind of like a nonlinear programming type of algorithm. Okay. All right, and so you just repeat this kind of over and over again, right? So how many times you repeat this? Well, it depends on the problem, but a lot of times it's not uncommon to repeat, especially for the types of problems we're going to do in biomechanics. It's probably not uncommon to repeat this, 10,000 times, 50,000 times, 100,000 times. And so the idea is that, when you repeat this over and over again, you take good guesses. And a lot of times these are not random guesses. Sometimes they are random guesses, but most algorithms are going to choose your design variables a little bit more intelligently, right? Eventually, you're going to converge on the optimal solution. Okay. All right. So this number should scare you, right? So the fact that we have to repeat this so many times. And so optimization usually is not something that you're going to do by hand. And so, usually the only thing that has the power to compute things this quickly, that fast, is to use some kind of computer programming code. Okay. So almost all modern optimization is done using computers. It's just the way the algorithms work, the way that we solve these problems is just usually not possible for a human to do unless you have 4 months to work out a calculation, which most people don't. So we're going to be using computers, so we're going to be using MATLAB for this, and you're going to see how this all kind of comes together. Okay. But that's generally how we solve these things. And so, we're not going to get into the details of how this is. And so we're basically going to allow MATLAB to do it for us. All we have to do is we have to set up the problem enough in order for the computer to kind of take over. So even though we're using computer code, it's not going to be completely automatic. We have to set up the problem for the code to run. Okay. Any questions on this? Okay. All right. So let's get back into biomechanics. Let me come zoom in back here. Okay. So let's apply everything that we've learned, to do a biomechanics optimization problem. Okay. And all we're going to do is we're all going to set up the problem, right? And we're going to start with a fairly simple example, which kind of has, well, one of the solutions is going to be fairly obvious. But we're going to use this to kind of take our concepts and just so you can kind of see it applied in a biomechanics context. Okay. Okay. So in this example here, let's do a muscle force optimization in the lower limb. Okay. So let's say that, from an inverse dynamics analysis, what we determine is that during a walking motion, um, there is a net plantar flexion moment of 100 Newton meters applied at the ankle. Oops. Okay. And so what this means is, so let me go ahead and draw a foot. Okay. So plantar flexion, remember, plantar flexion means that it's the motion where you're planting your toes into the ground. Okay. So that means the moment is going this way. Okay. And so it's a force that's going to push the toes into the ground. And so this has a magnitude of 100 Newton meters. Okay. All right. And so what we want to determine is we want to determine which muscles acting at the ankle are going to be acting in order to produce this moment. Okay. Okay. And so the next question is, which muscles act at the ankle joint that could contribute to this moment, right? So there are 5 muscles that act at the ankle. Right? Three of these are muscles that could produce a plantar flexion moment, and 2 of these are going to be for dorsiflexion. Okay. And so for each of these muscles, I'm going to give you the maximum amount of force that muscle can exert, as well as its moment time. So we're going to be given max muscle force and moment. Okay. So first we have the plantar flexion forces or muscles. So these are going to be the forces kind of in your calf muscle. Okay. So the first one is one of the main muscles in your calf, which is the gastrocnemius. Okay. So this is a plantar flexion. a plantar flexion muscle. It has a maximum muscle force of 4,097 newtons. Okay. And its moment arm, or in other words, the perpendicular distance between the muscle force and the ankle joint is 3.9 centimeters. Okay. Second muscle back there is the tibialis posterior. Okay. Once again, this is a plantar flexion moment muscle. This is a little bit of a smaller muscle, so it has a maximum force of only 3,052 newtons. Okay. And it has a moment arm of 0.8 centimeters. Okay. So this one attaches much closer to the ankle joint. All right, and the third muscle force, this one's also a plantar flexion muscle. We have the soleus muscle. Okay. It's also plantar flexion. This is the main muscle that's in your calf, so this is a much bigger muscle. So this can produce a maximum amount of 6,435 newtons, and its moment arm is 3.6 centimeters. Okay. Okay, so the next two muscles are dorsiflexion muscles. So these are going to be muscles actually on the front of your calves, okay, or your shin, I should say. Okay, so the first dorsiflexion muscle is a muscle that we haven't seen before, just because its name is very long. It's called the extensor digitorum longus. It's a very long name, right? So this is a dorsiflexion muscle, right? So this is a muscle that's primarily responsible for pointing your toes upwards. It's a very small muscle, so the muscles on the front of your shins are going to be much smaller than your calf muscles, just because these aren't used that much. So this only has a maximum muscle force of 801 newtons. Okay. And its moment arm is 4.2 centimeters. Okay. And then the last muscle that acts at your ankle is the tibialis anterior. Okay. Remember, anterior means front, and so this is a muscle that's on the front of your lower leg. Okay. This is a dorsiflexion muscle. Okay. It has a maximum muscle force of 1,207 newtons, and its moment arm is 4.5 centimeters. Okay, so those are the five main muscles that are acting at your ankle, right? So first thing you might ask is, wait a minute, we are, the net muscle force or the net muscle moment here is in plantar flexion. And so why are we bothering, with these dorsiflexion muscles? Okay. And so the first question to ask is, will the dorsiflexion muscles actually contribute to this motion, to this problem, right? Technically no. And so the dorsiflexion muscles, remember, muscles can only contract, and so they are not able to extend. And so, if you're going to ask, are they actually going to contribute to this 100 Newton meter moment? No, because it's physically impossible for them to do so. But that doesn't mean that they're dormant either, right? And so oftentimes, in these muscle force optimization problems, we include actually the opposing muscles as well, because even though they're not contributing to the motion, they do often contribute to joint stability. Okay. Because depending on the objective function that we choose, depending on the constraints that we choose, right? It could be that your three plantar flexion muscles are going to, maybe overcompensate or extend over the amount that's required. And so in order to cancel that out, your dorsiflexion muscles may need to contribute to kind of stabilize that moment or stabilize that force. Okay. Also, it's usually good for the opposing muscles to act as well, just because, if you have a completely dormant antagonist side, that can lead to some problems with dislocations and stuff like that. So there are ways for them to contribute, even though they don't contribute to the main motion. Okay. But with that said, for this problem, this is the first one that we're going to do. We're going to ignore their contributions just because we're going to try to keep this problem as simple as possible. Okay, and so we're going to ignore this and this. Okay. All right. And so that actually helps us out a lot because that cuts down the number of design variables from 5 to 3. Okay. And the thing with optimization, I'll say this again, optimization is not magic. And so, one thing that makes optimization really difficult is if you have a large number of design variables. Anyone in 454 will tell you that. And so, if there's ever a situation and if there's any way that you can cut down the number of design variables in your optimization problem, you should take it. And so in this case, reducing our number of variables from 5 to 3, that's a pretty big reduction. So that does save us quite a bit. That does save us quite a bit of work, for the optimization to do. Save us quite a bit of setup as well. Okay, but our three remaining design variables are, we have the gastrocnemius force. Okay. And we know that it has a maximum force of 4,097. And so the value, so we'll call the gastrocnemius force Fg. Okay. Fg has to be between 0 and 4,097. All right, our second design variable here is the force that's coming from the tibialis posterior muscle. And so we'll call this Ft. Based on its maximum amount of force, which is 3,052, we know the value of Ft has to be between 0 and 3,052. Okay. All right, and then the third design variable is our Soleus force. Okay. And so our Soleus force, that's our biggest one. And so we'll call this Fs. And Fs has to be between 0 and 6,435 newtons. Okay. All right. So there's some combination of these three forces, somewhere between their minimum and their maximum, that's going to satisfy this problem in the best way possible. Okay. Okay. So those are our design variables. So let's go over our constraints. Okay. So what are our constraints in this problem? The only piece of information we're given from the problem is that there has to be a net plant reflection moment of 100 Newton meters. Okay. Okay. That means the combination of all three of these forces must produce a net moment of 100 Newton meters. Okay. And so that means that the moment from the gastrocnemius plus, let me put the G above just to be consistent. Okay. Plus the moment from the tibialis posterior plus the moment from the soleus muscle has to be 100 Newton meters. Okay. And so we just need to add up all of their moment contributions. Okay. All right. So we can actually plug in for their moments because we are given their moment arms. Okay. And so the moment from the gastrocnemius force is going to be the gastrocnemius muscle force multiplied by its moment arm. And so the moment arm for the gastrocnemius force was 3.9 centimeters. And so if we convert that to meters, that is 0.039. Next, we have the moment from the tibialis posterior. And so that is Ft multiplied by its moment arm, which is 0.08. And so that's multiplied by 0.008 meters. Okay. And then we have the soleus force, and its moment arm is 3.6 centimeters, and so that's 0.036. Okay. Okay, so all these three adds up combined to a moment of 100 Newton meters. Okay. All right. And so that's the only piece of information we're given in this problem. And so technically we only have one equation here, right? This equation has to be satisfied because we know that the amount of moment is 100 Newton meters, right? We have one equation, but three unknowns, right? So if you think about it, this is kind of the exact situation that we had in our biostatics, right? But this time we're not given any information on the cross-sectional areas of the forces, so we have to come up with their values a different way. Okay. Okay. So this is the one equation that we are going to use to solve for the three unknowns, right? Well, that's not true. We're going to define an objective function in a bit, but this is the one equation that we have to satisfy. Okay. All right. Any questions on this example so far? Okay. All right. So let's get to our objective function. Okay. And so here we get to kind of an interesting point because we've basically made use of every single piece of information given to us in the problem. And so in the problem they told us that we have a net moment of 100 Newton meters. We're given all the different muscles that can contribute to this, which is their maximum force and their moment arms, and that's it. Okay, we've even already made an assumption here to simplify the problem. Okay. And so at this point, we have to kind of use our intuition a little bit, or we have to kind of use our know-how to come up with a way to solve this optimization problem. Okay. And so, usually, for a lot of optimization problems, the objective function is something that you come up with yourself. Right? Okay. which sounds very intimidating to do, but remember, we're the reason we're solving this problem is we want to come up with a combination of muscle forces that will best serve the body's needs. Okay? So we want to ask ourselves, okay? We want to ask ourselves what combinations of muscle forces, or I should say, what makes a good combination of muscle forces, okay? How would the body normally want to distribute this work in order to, do this in the most efficient or effective way possible? Okay? And so, what's the best way to split this task between our three muscles here in order to make it, more effective than others? Okay. Okay. So to do this, let's go back to kind of the very beginning of the lecture today, right? So what are some kind of motivations that that your body may do, or may use to come up with a good way to split this work? Okay. Right. So one thing that we talked about was energy consumption, right? So we want to, one way that the body determines, the best way to split up muscle forces is to minimize the amount of energy, minimize the amount of power that's consumed. So you can do this task in the most energy efficient way possible. Okay. Right. So that seems to make sense, right? So, if you're walking from point A to point B, which is, kind of what we're assuming that this situation represents, you don't want to exert, an excess amount of energy, right? Because you want to be able to walk for a long distance. Okay. Okay. So how do we quantify energy? Well, there's different ways that we can do this. So let's assume for a second that the total amount of energy is proportional to the total sum of all the muscle forces combined. Okay. So this seems to be a good starting point, right? Because if we think about the formula for work, right? Work is nothing more than just a force applied over a distance, right? And so in that case, energy and forces are directly linearly proportional to each other. Okay. And so what we can say is that our objective function is nothing more than just the sum of the forces. Okay. And so if we sum up Fg plus Ft plus Fs, okay. So whatever we determine for the gastrocnemius force, the tibialis posterior force, and the soleus force, we just add them up together. Okay. What we say is that this sum is going to be our objective function. Okay. And so usually the way that we denote this is that our objective function here is some function f, right? So this little function f, this is our objective function. Okay. Our objective function is a function of all of our design variables. So f is going to be a function of big Fg, big Ft, and big Fs. Okay. All right. And then what we want to do is we want to take this and we want to minimize its value as much as possible. Okay. We want to minimize the total value while still, adhering to the constraint. Okay. So we have our objective function, we have our constraint. And so remember, our constraint is, this guy right here. So this equation has to be satisfied, and we want to satisfy in a way that minimizes the value of this. Okay. Okay. Any questions on this so far? All right. So believe it or not, this problem that we have with this constraint and this objective function actually has a pretty straightforward solution. So we actually don't need an algorithm for this, okay? Because if our objective here is to minimize the total amount of force, right? If we look at the structure of our constraint here, right? Let's look at the moment, or let's look at the muscle that has the largest moment on, okay? So our gas shock Nevius force here has the most or the highest moment, right? And why is that significant, right? Because ultimately, whatever combination of the muscle forces that we choose has to produce 100 Newton meters of moment, right? And so for any moment equation, right, the force that you compute is nothing more than just the moment divided by its moment arm, right? So we have F is equal to M divided by D. Okay, for this D here is the moment arm. Right? And so if we want to minimize the total amount of force, right, what makes the most sense? And so if we want to minimize the total amount of force, the most sense is for the gas shock Nevius to do everything because that's the one with the largest moment arm. Right? Right? So if any other force contributes to the moment, right, it's going to require a higher amount of force, right? Because basically the further away the muscle is, the less, the further away the muscle acts from the pivot, right? The less amount of force that it has to exert to produce the same amount of moment, right? And so because the gas shock Nevius, one thing that you can say that has the most bang for its buck, right? So it's for every one Newton of gas shock Nevius force, that's going to produce more moment than 1 Newton of Soleus force, 1 Newton of the tibialis posterior. Okay. And so with this objective function, there's a fairly, I would say obvious solution. Okay. And so the obvious solution here is for the tibialis posterior force to do nothing, the Soleus force to do nothing, and then the gastrocnemius force, Fg, is going to be equal to 100 Newton meters divided by its moment arm, which is 0.0 0.039 meters. Okay. And we end up with a muscle force of 2564 newtons. Okay. All right, so let's do a quick check here to make sure that this 2564 is still within range. Okay. So if we go back to the start of the problem, we see the gastrocnemius force has a maximum of 4,097. So we're still within that range. Okay. So this solution here is technically valid, right? And so we satisfy the constraints. Our objective function is minimized, and we kind of just did this by inspection. Okay. So this result right here is not all that different from when we did statics, right? So when we did statics, we kind of assumed that one muscle force did everything, and that's essentially what we're having here, right? So, what's the deal, right? So, I kind of marketed optimization as, kind of a magic way to come up with, a combination of these muscle forces, but we end up with kind of where we started. Well, the problem was how we form our objective function here, right? So when we come back on Monday, what we're going to see is that, our solution here is going to change depending on how we formulate the objective function. And so formulating the objective function here is actually something very critically important for optimization. Okay. All right. Any final questions before we wrap it up for today? Okay, all right, so that's all we got time for today. So next time I see you guys will be Wednesday for the midterm exam, so please make sure you're here for that. If you have any questions on the homeworks or anything like that, I do have office hours after class today. And that's my last office hours actually. So if you want to talk to me again before the exam, you can always shoot me an email. We can make an appointment to talk, or whatever kind of works best for you. Okay. All right, so thank you guys for coming today. Hope you guys have a good rest of your day, and I will see you on Wednesday.
Yeah. And my question, like, calculated task code on this one.
Oh, yeah, so normally for these ones here, that's the distance between,
Or distance between on this department.
right. So but when you're multiplying the matrices, I've been telling people just don't worry about this one for that. So the way I got this was I multiplied, I believe it was, you transpose this matrix and multiply by this one because you want to get TCS up top
Yeah,
here.
the transpose on this one.
No, transpose this one. So
Transpose this one.
you transpose this one and then you multiply by this one, but then you
Yeah, I transpose this one and try this. I receive on this matrix and here.
yeah.
So
So the part you transpose is actually only this part right here. And then this part you kind of leave alone. So you transpose this and you leave this one alone, and you multiply by this one here. That's how you get that. But for the
yeah,
example,
if you want this code, this I code the better one.
yeah,
I give better one time the transpose matrix by
yeah,
transpose this.
uh-huh.
Yeah, after that, I told you R2
Yeah.
time with this one.
Oh, so when I say leave this one alone, so I would just transpose this one here,
Yeah, transpose.
and then we'll leave this part alone. And so so you still end up with a 3x3 matrix where the last column is still 39.1466.29 and we multiply by this one here. But for the multiplication one, so on the exam, I'm not going to make you multiply matrices. So you're just going to have to do parts 1 and 2. So yeah, don't worry about that last column. Yeah.
I go home and try to get this.
Okay, yeah. Yeah.
Problem 3.
Okay.
This is just like a sanity check.
Mhm.
So this is part A.
Okay.
So I have everything except for my signs right here.
Okay.
So to me, I thought everything for like the moments and stuff was just positive, but in the solution it says this one is negative and this one is negative. So here I have it broken down.
Mhm.
So I just figured like, okay, it's going like that. which is positive, right?
Yes.
But then it says negative in the solution.
I think what happened was, I think in the solutions, what I did was I assume it depends on how this leg is oriented. So if this leg is oriented like this, I think what I did in this, I kind of just, I rotated everything like this.
I did see that, okay.
Yeah, so the solutions may end up a little bit different, but as long as you're consistent with the sign conventions here, and it's consistent with your drawings. And so when I go to check these on the exam, I'm gonna check your equations relative to how you drew the problem.
Okay,
And so the way you drew it here and the signs that you have is perfectly consistent.
okay,
Yeah,
perfect.
I think what happened in my solution was I just had this rotated this way just because I just like drawing it that way for some reason.
That makes
And so that's
sense.
why these were reversed.
Okay, and then the other part, the example we did in class, it was pretty much similar to this setup. You used the 180 minus the theta.
Yep.
But in the solution, we just get rid of 180, so I'm figuring
Exactly.
it just doesn't matter which way you.
Yeah, so
rotate it.
I usually use the acute angle, so that's why I rotated that way, just to make sure theta one there was the acute angle. Because when you're using trig, usually I like to use the acute one, but if you're going to use it, but I think if it's drawn this way, then I would do it just like you did with the 180 minus theta.
Oh, okay, so if it's an acute angle, then use the 180.
Exactly, so because this one's tilted this way, and the theta one that's given to you is on this side, so this is the obtuse angle, I would definitely use the 180 minus theta, because that one is, it's more straightforward to use the trig.
Okay, and then everything else was acute, so we just left it as.
Exactly.
theta 2. Okay,
Yeah.
perfect,
Mhm.
thank you so much.
Yeah.
I had some math, but I'll ask in office.
Okay, sounds good.